Right. Good morning, everybody. Let's go ahead and get started. Let me see your hand if you can hear me. Okay, perfect. So two of you, Darius and Jonathan, thank you for responding. A couple of quick announcements. The first thing is a note for me to start recording, which I already did. The second thing is, as you requested and as I promised in the previous spring semester, the class videos um, of our 8 o'clock class section are being recorded and they're being uploaded to YouTube. Okay, the link to all of that is on Moodle site. Okay, so just log on to Moodle and then the link to YouTube playlist is available right there. I'm um, posting all the class videos after each class, probably by the end of the day. Okay. All right. So let's begin. Questions, please. Questions so far. Okay. So let's quickly review what we did in the last class. We started chapter 4 in the last class. Okay. We started with chapter 4, which is mainly techniques of circuit analysis. Before we went into the different techniques, I showed you how to use MATLAB. How do you download MATLAB and how you can set up the so-called MATLAB code. Okay, just 3 or 4 simple lines of code that can be used to help you solve system of simultaneous linear equations. Okay, this is something we started talking about. Then we discussed a few nomenclature, a few terminology, node voltage method, mesh current method, source transformations are the big techniques that we will learn in this class. And in that context, a node is a point where circuit elements join. A reference node is often, we define the reference node at the beginning of the problem to be the um, voltage node that is at the lowest potential or assumed to be at the lowest potential. Okay, typically we call that ground. Then a loop is a path through which uh, a path which begins and ends at the same node. And then of course there's a mesh, which is a subset of a loop. A mesh is a loop that does not enclose any other loops. Okay, so the problems, the techniques that we solved, that we looked at, revolved around mesh current method, which is an application of KVL, or a node voltage method, which is simply an application of KCL at different nodes. Okay, KCL at nodes. Mesh current method is KVL around loops, around different mesh. Okay, so in relation to that, we looked at a bunch of problems. We looked at a couple of problems. I showed you the generic approach. Okay, the idea that we looked at was to step one, we start by finding a reference node, and then the step two was to identify different nodes, set up node voltages. Then the next step is to write KCL at each node and then solve the resulting system of linear equations to arrive at the answers for unknowns. Typically, as I mentioned in the last class, the number of, and through previous classes, the number of unknowns should equal the number of equations.
Professor, can you going back up to that example circuit that's drawn just up there, where you identify the ground node in step one, what
Yes.
what designates that one as the ground node?
Well, what I see is that there are um, a bunch of uh, elements originating from that node. So I do not see any other potential. So if you think about it, all of these, the bottom of all of these terminals, it's as if they're all bunched together into one connection. So even though it appears like there's one, two, three, four nodes, it's all one connection. And then it would seem that all of the elements are emanating from that single node. Naturally, I pick that as a reference or a ground node.
Oh, I see. Okay, so that's up to the user to decide which one.
Yes, yes, I can use any other node as a reference node
Okay.
as well if I so choose. Okay. Other questions, please. It's a good question. Thank you. All right. So that's what we discussed. We looked at a couple of examples. The second example, using, where did that go? Okay. Using node voltage method, when I have a dependent voltage source or a dependent current source. Okay. This is something, it's an example that we looked at as well. Did we or did we not? We did not look at this example. Maybe we can solve this example. Okay, so in addition to that, okay, we looked at mesh current method. Okay, so here is another example of node voltage method where I encountered a dependent voltage source. Okay, a dependent voltage source. You can treat that dependent variable as a third unknown and set up an equation that determines the third unknown. Okay, so in this case, I phi is V1 minus V2 over 5 ohms. And that is enough to resolve the unknown I phi, okay, using the equations at least. So there's more than one ways to do that. Okay. Now, let's see. So that's about the node voltage method. Then we looked at the mesh current method. Mesh current method is an application of KVL, Kirchhoff's voltage law. Okay, we define three different mesh here: mesh 1, mesh 2, and mesh 3 as shown there, and then write KVL around the loops. We pay particular attention to these elements, this guy, because there are two different currents flowing in here. There is I1 from the left mesh, there is I2 from the right mesh. Similarly, I pay particular attention to this guy because there's two different currents flowing in there. There is I2 from the left mesh flowing in that direction, and there's also I3 flowing in the same resistance. So we once we pay particular attention, we account for both the currents flowing in opposite directions, mutually opposite directions. Then it's easy to write KVL for all of these. So at this point, we could move forward and look at some of the some of the other techniques like source transformations, but I don't want to do that, particularly because this is not going to be, chapter 4 is not going to be on the midterm. Owing to that fact, I don't want to overextend myself before the midterm. So in this class, what we are going to do is to spend some more time on the node voltage and mesh current methods. Particularly, I want to spend some time on a couple of example problems, node voltage method problems. This guy I have up here. Okay, and in order to do that, I need your help. Okay, I want to make sure that you participate in this, and then you kind of drive the discussion in terms of how to begin the problem and where to go next. Okay, so for example, let's start by working on this problem. Okay, and I look for volunteers, and what you can do as a matter of fact is to take a sheet of paper and then start working on this problem yourself. Why don't I give you 5 minutes to start working on the problems? Then maybe I'll come back and pick on a couple of you to get us started. Okay, so start working on the problem for about 5 minutes. I'm going to let you work on this problem. So before I go silent, let's quickly look at the problem. There is a circuit here, okay, with a bunch of different branches, bunch of different nodes. And then the problem that we are supposed to solve is to use node voltage method. And we are expected to find the total power developed in this circuit. Okay, the total power developed in this circuit, that's going to be coming from two sources. Okay, from two sources. Then the second part of the problem goes on to ask us to um, find the total power absorbed in this circuit. So we have to pay particular attention to passive source convention. Okay, the idea that the power sources could be delivering or absorbing power. Okay, so in order to do that, the first step would be to find all the currents. Okay, if I find the current and the voltage in each of these nodes, okay, then it should be easy for me to multiply the power, the voltage times current in each of the element, and then um, add them up appropriately to find the total power absorbed or delivered, and see that the total power delivered is exactly equals to the total power absorbed. Okay, so that's the idea. So the first step is to use node voltage method to find all the node voltages and branch currents. Okay, so I'll go silent now for exactly 5 minutes, then come back, and please be prepared to volunteer and get the problem going as a discussion section. To get started with this problem.
Yes.
Okay, do you want to get us started, Darius?
Yes, I want to make sure that I was setting this up right because I want to start with the whole loop. I want to go all the way around, um, making the current going out from each node I1, I2, I3, respectively.
Sure. So do you want to pick a reference node?
Can we use the um, does it matter if I use the one above the 40 ohm resistor, that first
This
node
guy
right there?
right here?
Yes.
It doesn't, but the convention is to use this guy as the reference node.
Okay, then let's use the bottom as a reference node.
Okay. Okay.
And I want to make sure I'm getting the sign conventions right. So if we know that the source 25 amps is going into each one of these nodes, except for at least on the top, and then on the bottom they're going the same direction. The signs should all be the same, correct?
You could define the signs arbitrarily. So do you want to pick a positive on the top and negative on the bottom for the
Yes,
40 ohm resistance?
I wanted to make sure that if I did that, that it would not cause any problems setting up the KCL.
No, it won't. It won't cause any problems.
Okay, that's what I was thinking.
Yeah. It doesn't matter even if you pick the opposite. Even if you said this is negative and this is positive, it should still come back to give you the right solution. Just that it is convention to pick the current flowing direction, that guy to be positive and this guy to be negative.
But as long as we were setting up the KCL is equal to 0, the convention of the sign should still balance out, correct?
It should balance out eventually, correct?
Okay.
So did you say you want to pick positive to negative from all of these, right?
Correct. Yep.
Right
Just
here.
like that. Just like that.
Okay, so I picked the sign for 40 ohm, 160 ohm, and 20 ohm resistances. And then we'll worry about this 10 ohm resistance and the 8 ohm resistance, the sign for that at a later time. Okay, so sure, what else? What would be the next step?
Now, wouldn't we be summing the entirety of the current in these loops to solve, to use KCL?
Sure. When we are doing the K, this is the node voltage method, right?
Yes. Oh, excuse me. KVL.
This is the node voltage method. So we use KCL at different nodes. Okay, so the next step would be, like you pointed out, to go around the circuit and identify different nodes. Okay, so if I can go back, I listed the steps that I want to do here. The first step is to identify the ground node. Then the next step is to identify different nodes. Remember, I have done node 1, I named a node 2, so on and so forth. So my next step would be to go through this branch and identify the different node, go through this circuit and identify different nodes.
Yes, and I did, just node 1 through 6 from the top left going around.
So you call this node 1,
Correct.
node 2, 3, 4, 5, 6.
Yes.
Is that what you did?
Yes,
Sure.
sir.
Good.
Should only need 3 nodes, right? The top 3.
We should only need 2 or 3 nodes. Let's see. There's 1, 2, 3. Let's start with what you have, and then we'll go about reducing the number of nodes. Now, if you think about it, even though number 4 and 5 and 6 seem like they're different, they're really all one node. Okay? If there was a different element in between these two nodes, then they would be independent nodes. But given the fact that they're all shorted, there's no voltage drop across them, would you be okay, Darius, if I considered all of this as a single node?
Yes, you can. I just want to clarify, for the sake of these circuits, when you say there is no voltage drop, we are assuming in a perfect circuit. However, in reality, if I am calculating a replacement wire, I specifically have to take into account voltage drop.
Yes.
Right?
Yes.
Okay.
I appreciate you being very diligent about it and you're being very thoughtful about it. So here for now, we are going to assume that this wire is a perfect short with 0 resistance.
Okay.
And under that assumption, would you permit me to call all of these nodes a single node?
Oh yeah, let's make it simple.
Okay, perfect. Now, by the same token, in the same argument, I'm going to combine these two nodes as well. because there is no circuit element here, there's a perfect short. I'm going to simply combine all of this and say, this is all one node. Okay. All right. Questions about that so far, please? Okay. So the idea is, so I have come up with two nodes now then. So the first step was to find the, let me go back to black. First step was to find the ground node. The second step is to find the identify the independent nodes. Okay, in this case, I have done that. I identified 6 nodes to begin with, and then I simplified based on the assumption that this is a perfect shot. Okay, so that's I'm left with 2 independent nodes. What's the next step? What would be my next step?
At this point, can we start setting up the equation and calculate voltage across at least node 1 and 2?
Yes, so you want to do KCL at node 1, right? So in order to do that, let's look at all the currents leaving that node. So my node is this guy, right? And I'm interested in adding all the currents leaving that node, okay, which is this node is the same as node 1, right? So what else? What other branches did I not take into account yet?
The one on the right with the 10 ohm resistor.
So that's the current leaving the branch here. And what else? Seems there's one branch current that I have not accounted for yet.
Is it the current source?
Yes, it's the current source. And then by convention, what I'm doing is I'm looking at the current leaving the node. So I'm going to consider the opposite direction for the current source. Okay, now my next step would be to look at all of these currents, to sum these. There is current 1, current 2, current 3, current 4. So KCL at node 1 means I1 plus I2 plus I3 plus I4, all of that is equals to 0. So what is I1? I1 is the exact opposite of my current source. So I have a negative 25 amperes because the correct direction I have chosen here is the exact opposite of the actual current direction. Okay, does that make sense? Okay, so this guy is negative 25 amperes. What's the next value? What's the current flowing in this branch through 40 ohm resistance?
25 amps times the 40 ohm resistance.
25 ampere times the 40 ohm resistance? Could be, could not be. If you think about it.
Would it be the voltage at node 1 minus 0 divided by 40?
Yes, it will not be 25 amperes. The reason is the 25 amperes that is coming here is not all flowing through here. It's being split into 2 branches. So I don't know what fraction of 25 is going in there. So I cannot quite make that leap. Okay. So if that's what the only branch I could do that. So I2 would be the voltage here, which is V1, because that's at node 1, right? It's all node 1. So V1, this voltage, minus this voltage, which is assumed to be ground, over 40 ohms. That's the Ohm's law, right? The Ohm's law is the potential difference between the two terminals of the resistance divided by the value of the resistance, magnitude of the resistance. Okay, so let's do the same thing for I3 as well.
Can we
What
call
would be the,
I delta just to follow the convention of the illustration that we have up here in the figure?
can you say that again?
Our I3, can we change that to I delta just to follow the convention of the figure?
Sorry about that. We can pick I delta to be this guy. Okay, so I'm going to modify my equation accordingly to incorporate a delta here. Okay, sure.
So then I delta will just be V1 minus 0 divided by 160 ohms.
Correct. And I4, what would I4 be?
V1 minus V2 divided by 10 ohms.
V1 minus V2 divided by 10 ohms. All of that should sum to 0. So that's my KCL at node 1. So you can go through some gymnastics. You can go through massaging the equation a little bit. And then I don't know. Let's see. What is the eventual equation? I just want to give you the equation that you get after going through the algebraic manipulation. So it will be V1 times 21 plus V2 times the negative 16 plus I delta times 0. All of that is going to be 4,000. Okay, so that's the idea of KCL at node 1. Okay, so KCL at node 1. So let me clean this up a little bit. Okay. And then let's do KCL at node 2 as well. Okay, it's the best way for me to include all of this in one. Okay, so KCL at node 2. Who wants to get us started? So at node 2, I'm going to redefine the current directions. Okay, I'm going to, or maybe I can leave them in there like so. Okay, I'm going to redefine just this I4. Okay, just the direction of the I4 to be that I. Okay, and then there's a current flowing in this direction, and there's a current flowing in this direction. Okay, there are three currents at that node I2. Okay, at node I2, there are three branches, and as a result, there are three currents leaving those branches. Okay, so do you want to, who wants to help me set up the KCL at node 2?
Somebody answered in the chat, sir.
Could you read that out to me, please? I don't have that on
He
my
just
screen.
said V2 minus V1 divided by 10 for our I4, I believe.
Correct. So I'm going to call this I don't know, I4. I can still call it I4, but I just don't want to. Let's call this
Could we have defined it as just negative I4 and called it negative whatever we originally found for I4, or is that not the thing?
We could do that. We could do that. So instead of, so in other words, let me park this to one side. Okay. So what I have done was current leaving in all the branches. So let me call this I negative I4. Okay. Plus I5 plus I6. is 0. That's what you wanted to do, right? You wanted to say, I will call it negative I4, right?
Yeah, that's what I was wondering if that was a possible thing.
That is exactly what I'm doing here. So think about this. This is I4, V1 minus V2. And what is this guy? V2 minus V1. That's exactly negative I4, right?
Or
So no matter how you look at it, no matter how you slice it, you still get the exact same thing. So this is the negative of that guy. Okay, so you could do that. You could very well call this negative I4 and add that.
all right. And then for I5, we have V2 minus 0 divided by 20 ohms. And for I6, we have V2 minus 84 I delta divided by 8 ohms.
Correct. So it seems there is a third unknown variable here. So there are V1 is an unknown, V2 is an unknown, and it seems there's a third unknown here, V1, V2, and there's an I delta unknown here. So in order to understand I delta, I'd simply have to make use of this dependence here. I delta is V1 over 160. Okay, so I delta is V1 over V1 minus 0 over 160. So that's the third equation that I would need to take into account. But before that, let me see if I can give you the simplified version of the second equation. Okay, the second equation is going to be V1 times negative 4 plus V2 times 11 plus I delta times negative 420. All of that is 0. That's equation number 2. Okay, so the third equation is I delta is V2, V1, is it V1? V1 over 160. Or to put it in a familiar form, V1 times 1 plus V2 times 0 plus I delta times negative 160 equals to 0. So I have 3 equations here and 3 unknowns. So let me put them all, bring them all together. So 3 equations, 3 unknowns, I can plug them into MATLAB. That's my equation 1. That's my equation 2. That's my equation 3. Okay, so 3 unknowns, 1, 2, and 3. 3 equations. We're good to go. Plug them into MATLAB. And then you should get values. Well, I leave that as an exercise to you. Okay, leave that as an exercise.
Sir, I'm sorry. I looked away for half a second. Where did the third equation come from?
The third equation came from this guy. Okay, from the observation that you look at this, I delta is V1 minus 0 volts over the 160 ohm resistance. So it's an application of Ohm's law across the 160 ohm resistance. Okay, so I delta times 160, I just rearranged this guy. So there's a factor of 1 for V1. There's a factor of negative 160 for I delta, and there's no V2 in that equation. So third equation is simply a rearrangement of this guy, which is nothing but Ohm's law.
Perfect. Thank you.
Yeah. All right, other questions, please. All right, this is fun, isn't it? So let's do one more problem. This time we'll do the mesh current method. Let's do the mesh current method. Okay, and we'll do something interesting here. We'll take a problem. We'll solve the problem using mesh current method and solve the exact problem using node voltage method. And in theory, both of these should lead us to the same solution, and they will. They will lead us to the same solution. So let's get started with another problem. Okay. So everybody on the same page with the first problem, right?
Yes, sir.
Okay. So let's go here. Maybe not there. Let's see. Okay. So I'm going to do that. Okay. Copy this guy. Let's see. Go here. Chapter 4. So node voltage method. Mesh current. Okay. Mesh current method. So what I want you to do is to take about 5 minutes to start working on this problem. And then what you will do is you'll apply the mesh current method. So the first step is to identify independent mesh, all the mesh. The next step is to identify the mesh currents, IA, IB, and IC. I don't know, it appears to me that there are 3 independent mesh components in here. So I identify IA, IB, and IC through to be mesh currents. The next step would be to set up KVL around each mesh. Okay, so before I go silent again, this is what I'm going to do. I'm going to go back to the previous problem, okay, and leave you with what you should be doing. You put them into MATLAB and get the values for V1, V2, V3, or I delta. V1, V2, and I delta, right? Once you have the values for V1, V2, I delta, it should be a straightforward exercise to calculate the current through each of these resistances. Okay, for example, if I wanted to look at the current through the 20 ohm resistance, okay, I would simply have to do V2 minus 0 over 20. That will give me the current in the 20 ohm resistance. So the current times the voltage across that gives me the power. So I do the exact same thing. I calculate power through all of these resistances. I calculate power through the voltage source at the right and the current source in the left, and then add them up all together. All the absorbed current to one side, delivered current to one side, and you'll see that the power delivered equals to the power absorbed. Okay, so there's a little bit of a gap I'm leaving here in terms of the MATLAB and in terms of calculating the powers. All right, why don't you go ahead and get started with the mesh current method. I identify the steps that you want to follow. So in about 5 minutes, we'll come back and work on this problem. All right, let's resume. So any volunteers to get us started with this problem?
Yeah, I can do it.
Sure.
So I started by choosing my 3 loops or my 3 meshes.
Okay.
So there's 3 kind of obvious ones. So I labeled the top left loop my mesh 1, bottom left mesh 2, and then the large one mesh 3.
Okay. So let me catch up with you. Give me a second. So there's this guy, 1, and then there's this guy, the one on the bottom, that's number 2. And then you said the one on the right, this guy to be the 3rd one, right?
Yes.
Okay, yeah,
So then I also identified the currents, and I just stuck with clockwise convention on all 3.
good.
So,
And did you call them IA, IB, and IC as well?
I called them 1, 2, and 3. I didn't realize
Okay.
A, B, and C, but same thing. So 1 will be A, 2 is B, 3 is C.
Sure, sure. So it's fine with me if you want to go with 1, 2, and 3. I just chose A, B, and C because I don't want to confuse them with 1, 2, and 3 over here.
Ah, okay. I didn't
Okay.
even
So is it,
realize those were there. Honestly, I didn't see that.
yeah. Is it all right if I went with A, B, and C?
Of course, yeah.
Okay. So that's step 1 done. That's step 2 done. Then what? So KVL around mesh 1, which is this guy, all right? So this is all mesh 1.
Right. So we start from the middle left node, right underneath our very first voltage supply, and work our way around mesh 1.
Okay. Sure.
We'll have a negative 125. I'm sorry, this is for the KVL. So we would have negative 125 plus 1 ohm times IA plus 6 ohms times IA. And then I believe it's minus 6 ohms times IC.
That's very correct. And do you want to go over why that is the case?
The way I see it is just you have the current from mesh 3 and the current from mesh 1 crossing the same resistor at the same time. So you have to account for that. That's my
Yes,
understanding.
that's a very very cogent way to put it.
And then let's see. And then you have plus 2 ohms times IA minus 2 ohms times I2, and that all equates to 0. Oh, I'm sorry, IB. I'm sorry. Yeah, and that all
You're
equates
fine.
to 0.
I got that. So let me write this a little better.
And then I'll leave the other 2 meshes for somebody else if that's okay. I can continue
Of
if you
course.
like, though.
Yes.
If nobody else steps up, I can keep going.
Okay. So any volunteers to do the KVL around mesh 2?
Is it minus 125 plus IB times 2?
Minus 125 plus
Plus
IB times 2 ohms. Yes.
plus IB times 12.
Plus IB times, oops, hold on 1 second, sorry. Okay. Plus IB times 12 ohms. Okay. So that's this guy,
minus,
right?
yeah, minus IC times 12.
Minus IC times 12.
Plus IB times 1.
Plus IB times 1 ohm. All of that equals
And
0.
And I forgot. I believe it's minus IA times 2.
Minus IA times 2 ohms. Okay, all of that is 0. So second equation, do you want to do the third one or do you want to pass?
If no one else wants to do it, then I can do it.
Okay, let's throw it out there and see if the if any volunteers are there to do KVL around mesh 3.
I can do it.
Yes.
Let's see. For the first one, we have IC times 12 ohms.
Okay, just give me a second so I catch up with you. Okay, IC times 12 ohms, is it?
Yes.
So IC times 12 ohms, sure.
And then minus IB times 12 ohms
Okay,
plus IC times 6 ohms minus IA times 6 ohms and then plus IC times 24 ohms.
so there are 3 equations here, 3 unknowns, and let me see if I can put this in an equation format that works for MATLAB. Let's see I1 or IA times 9 plus I2 times negative 2 or IB times negative 2 plus IC times negative 6. All of that is 125. So this is IA times 9 plus IB times, so this is equation 1. IA times negative 6. Now that's, so this is negative 2 plus IB times 15 plus IC times negative 12 is 125 as well. It's the second equation. Third equation comes out to be IA times negative 6 plus IB times negative 12 plus I3 times 42. All of that equals to 0. That's number 3. Okay, 3 equations. Solve for the equations. I1 should come out to be 23.756 amperes. Okay, I2 is 18.428 amperes, and I3 will come out to be 8.659 amperes. Okay, so a straightforward exercise once we know the different steps that we want to follow. Okay, so this is mesh 2 and this is mesh 3. Okay, so do you want to solve the exact problem using KVL, node voltage analysis as well?
That would be interesting.
Okay, so do you want to get us started then? Any volunteers to get us started?
I suppose we'd start by choosing a ground.
Sure.
So I suppose a good spot would just be bottom center.
Sure. You can use that guy as the reference node. And that would be a reasonable node because it seems there's 1, there's 2, there is 3 different elements emanating from that node. Okay. Doesn't matter. I might as well have chosen this node or any other node to be my reference. Okay, so the next step, so the first step is that guy. The next step would be to identify the different nodes.
Correct. So I guess we could do a node in the top middle in between the 1 ohm and 6 ohm resistor.
Okay, we'll call this number 2. Call this number 3. If you think about it, another good reference potential could be this guy as well, because there are 2 power supplies that are connected to this node. So it's almost always they need to have a pretty good reference to go off of. I might as well have picked that guy as my reference node. Okay.
Would you prefer to do that